Okay, so today we will introduce some more definitions, okay? And then we will start solving some exercises to see what type of problems we should expect in our upcoming assignments and exams. So, one more definition that I didn't introduce yet is atomic packing factor. So in whatever way the constituent atoms are packed, there is always some free space in the form of voids. The fraction of the total space in the unit cell occupied by the constituent particles is called atomic packing fraction or atomic packing factor. The way I want you to think of the packing factor is as follows. Imagine you have a box and imagine you have spheres that you want to put inside the box. Okay, the atomic packing factor or the atomic packing fraction is the volume of the spheres inside the box divided by the volume of the box. In whatever way you put these spheres inside the box, there will always be some free space. Okay, if there is no free space whatsoever, the atomic packing factor will be 1. If the volume of the atoms in the box is equal to the volume of the box, then the atomic packing factor will be 1. But this can never happen in case of spheres, okay? Just imagine it again, you bring a box and you wanna put spheres inside the box, okay? In whichever way you pack the spheres inside the box, there will always be some free space. There will always be some free space. And this is why we introduced this atomic packing factor to say it is the volume of the atoms inside the box divided by the volume of the box. Okay, so in case of the spheres and in case of the unit cell, the atomic packing factor is N, which is the number of spheres or the number of atoms inside the unit cell, times the volume of one sphere, which is always 4/3πr², divided by the volume of the unit cell. So you need to look at your unit cell and see what is its volume. And then this is how you calculate your atomic packing factor. So the atomic packing factor will always be less than 1 because there will always be some free space, okay? Because there is some free space implies the volume of the atoms in the box is less than the volume of the box, which means this thing over here is less than 1. Okay, so the atomic packing factor is less than 1. Let's look at particular examples, and I want you to focus here. So, in a cubic P lattice, that is in a simple cubic lattice, this is how a conventional unit cell look like. Okay, this is how a conventional unit cell look like. And the volume of this conventional unit cell is, so the volume of the unit cell is equal to the side of the cell cube, because this is a cube. So its volume is a cube. Okay, so we are done with whatever is in the denominator, which is the volume of the unit cell. Now, in reality, when we pack atoms in the in this unit cell, they will look something like this. These balls over here will touch each other. Okay, these balls over here will touch each other. So we will see something like this in reality. Okay, so we will see that these balls here are touching each other, these balls are touching each other, these balls are touching each other. So here we want to calculate the atomic packing factor. So the atomic packing factor is N. What is N in case of a cubic P? What is N in case of a simple cubic or a cubic P? N is 1, if you remember. We have, what is N? N is the number of atoms per unit cell. And in a simple cubic, if you look here, it's clear actually. If you look here, it's very clear. We have 8 corners, and each corner share 1/8 of a sphere. So we have 1. So N is equal to 1. We are done with this. We have the volume of the unit cell is a cube. Okay. Now we want to find, because here, if I want to work this out, instead of N, I will put 1. Here I have R and I have A. I need to find a relationship between A and R. And this will solve the problem for me. Okay, if I find a relationship between A and R, this will solve the problem for me. So now I want you to look here. Let's take this point over here to be A, and let's take this point over here to be B. Okay, now this distance AB in terms of A, how much is it? This AB in terms of A, where A is the edge of the cube. How much is AB? It is A, right? It is the full edge of the cube. Now, in terms of R, how much is this AB in terms of R? How much is it? Let's count. Okay, how much is this from here to here? How much is this distance from here to here? From here to here, how much is it? This is R. And then there is this distance from here to here. It's another R. So AB is also 2R. So AB is A and AB is 2R. So I have A equal to R, or R is equal A over 2. Now I come to this equation for the atomic packing factor. I put 1 for M. I put A over 2 for R. I keep this A over here. And then I get the atomic packing factor. If I plug whatever I want to plug. So the atomic packing factor, I put A over 2 for R. Okay. I will get the answer here. You just use a calculator. A cube will cancel the A cube. And then I have 1 times 4 over 3 pi divided by 2 cube. And this will give me the atomic packing factor in a simple cubic lattice to be 0.52. Notice that there is lots of free space. It's almost half. There is lots of free space. It's almost half. This is why we mentioned in the very beginning that this is not a very stable configuration. Do you remember how many atoms have this configuration, the simple cubic? There's only one, and that's polonium. Okay, let's take another example. Let's take another example. That of a BCC, the body-centered cubic. So this is how a conventional unit cell look like. Again, it's a cube. So A, so the volume is it just a cube? Okay. So down here, the volume of the unit cell is a cube. Okay. So down here we are done. Now, how many atoms are there in a conventional unit cell of a BCC? So remember, this is my conventional unit cell. I have 1 atom shared by all the 8 corners. So I have 1, and there is 1 in the middle. So I have 2. So this N over here is 2. We are done with it. Now I want to find a relationship between A and R so as I can work with this equation. Okay. Now, what happens in reality, so this is just a schematic in order to see it clearly, but when we really put hard sphere models, now we see these, for example, if we look on the top layer, no one is touching anyone. The same thing if I look on the side layer and the down layer on the other side layer, okay, on the phases. The atoms do not touch each other on the on all 6 faces. They don't touch each other. When are they touching each other? The atoms are touching each other here. You see, if we take the big diagonal, which is inside the cube. So imagine here I have this thing here. So this is 1, the big sphere over here, the big sphere which is in the middle. Okay, and then part of this one over here. These 3 are touching each other. These 3 are touching each other. Now, so let's call this AB again. So we call this AB again. And how much is AB? AB in terms of R, okay? So from here it is R, then from the big cube, from the big sphere in the middle, it takes the whole diameter, so it is 2R. Then it takes only 1R from this portion over here. So this is equal 4R, okay? So this is equal 4R. Now, if I want to calculate it in terms of this edge A, because this side over here is A, here you need to prove it yourselves that AB is A square root of 3. Okay, this is A. It's A square root of 3. Okay, so here in order to prove it yourselves, you just Google it. What is the length of the long diagonal inside a cube? Okay, and you will find derivations everywhere where it shows you that the long diagonal inside the cube is A square root of 3. So now I have 4R is equal to A square root of 3, or R is equal A over 4 square root of 3. Okay? And we know that N is equal to 2. So now instead of R, I put A over 4 square root of 3, and A, I keep it, and I put 2, and I find the answer. You find it here. Okay, so I just plugged instead of R, A radical 3 over 4. And you find the atomic packing factor to be 0.68. Notice that the atomic packing factor in case of BCC is slightly higher than that of the simple cubic, okay? And that's also what we mentioned when we were discussing this. We said that this configuration is more stable because the void in the middle is filled. Okay, now if we want to calculate that of FCC, do we consider the number to be higher or lower? It will be higher because when we discussed this, we said that the FCC is the best pack, the most efficient stacking of balls. So let's look at it. So this is the case of the FCC. We have 8 corners filled with atoms, and then we have all the faces filled with atoms as well. Now, if we combine them and we look here where it's clear, we are only looking at one unit cell, okay? Where are the atoms touching each other? They are touching here, here, right here. On all faces, they are touching. On all faces, they are touching, okay? So now let me just focus on one of them, so as you don't get confused. Let's take any one of them. So let's, for example, take this one, and let's call this here A, and this one here B, okay? So how much is AB in terms of R? It is R plus 2R plus R. So again, it's R plus 2R plus R, and this gives me 4R. And how much is AB in terms of A? If you look here at this right triangle, you have this side here A, this side here A. Pythagoras theorem will give you that this side, so let me just show you about which sides I'm talking. I'm talking about this side and this side. This triangle here drawn with the red side, this is a right triangle right at this corner over here. This is A, and this is A, and this is A. So Pythagoras theorem, this side is A square root of 2, okay, which is square root of A square plus A square, and that's A square root of 2. So I get that R is R is A square root of 2 divided by 4, okay? And I also need N. How much is N in case of an FCC? Remember, I have all 8 corners occupied by only 1, so that's 1. Then I have all 6 faces sharing only half of them, right? Because the other half is taken to the other side. So I have 1 plus 3, and that's 4. So N is 4, R is A square root 2 over 4, and the volume of the cube, we still have a cube, so the volume is A cube. And then if you plug all the numbers, you get the atomic packing factor to be 0.74, which is indeed much higher than that of the BCC and much higher than that of the simple cube. Okay, now I'm gonna make a very quick revision. So in this chapter, there are lots of mathematical formulas that you need to review, okay? So some of them I will be reviewing with you, but other things I will just say that you need to review on your own, okay? And all these things are usually stuff you have taken in high school, yeah, in high school. So even if you haven't taken during university time, you have taken in high school. And these days, it's super easy just to Google something like dot product of 2 vectors, and then you can get all the information you want. But now I'm doing the revision with you for the dot product because there is a problem I want to solve with you, but we cannot solve it if we don't review the dot product. So consider 2 vectors in 3D. Vector A has components A1, A2, A3, and vector B has components B1, B2, and B3. The dot product of vector A dot B, or A dot product B, or A dot B is equal the absolute value of vector A, that is the length of vector A, times the absolute value of vector B, that is the length of vector B, times the cosine, the angle between the 2 vectors, okay? I can write this in another way. Cosine theta is equal to A dot B, that is the dot product of the 2 vectors, divided by the absolute value of A times the absolute value of B. And this is an equation that I use if I want to find the angle between 2 vectors. So if I give you 2 vectors, for example, here A and B, and I tell you find the angle between them. So to find the angle between them, you have to find the dot product of the 2 vectors and you divide by the length of each of them. And what is the dot product of 2 vectors? The dot product of 2 vectors is as simple as this. If vector A is A1, A2, A3, vector B is B1, B2, B3, the dot product is an algebraic number. It's a number, it's not a vector. And it's simply A1, B1 plus A2, B2 plus A3, B3. Okay? So here is an example here. If I have vector A, which is 1, 2, 3, and vector B is 4, minus 5, 6, then cosine theta is equal to A dot B, which is 1 times 4, plus 2 times minus 5, plus 3 times 6. And this gives me on the numerator 4 minus 10 plus 18, okay, divided by the length of vector A, which has components 1, 2, 3, and the length of any vector, the length of a vector is equal to absolute value of the first component, so A1 square plus A2 square plus A3 square. So this is if I'm getting the length of vector A1. Okay, so this is the formula. Now, if I have this vector A1, 2, 3, implies it is the it's the square root. I got confused between. Okay, so it's the square root of this. So it's the square root of 1 plus 2 square, which is 4, plus 3 square, which is 9. Okay, and then I have to multiply it by the length of vector B, which happens to be the square root of 4 square plus minus 5 square, then it is 25. The minus will cancel with the square, and then 6 square is 36. And now if I just do the math, 4 minus 10 plus 18 is 12, divided by, I just use a calculator here, I get cosine theta equals 0.36, or theta is equal to 70. Okay, so please keep this again in mind. If I have two vectors and I want to find the angle between them, I take the dot product and I divide by the absolute value of both. Okay, so now why I'm doing this? Because I want to solve this exercise. So consider a body-centered cubic lattice with a lattice constant A. Okay, so consider this BCC lattice with a lattice constant A. Okay, that is the side of the cube is A. This is what it means by saying lattice constant A. So it means the side of the cube is equal to A. Okay, now find the angle between each two primitive lattices. Actually here, not two primitive lattices. This is two lattice vectors. So two primitive lattice vectors. There's vectors here. Okay. Given that the lattice vectors are A1, A2, and A3. When we discussed BCC vectors in class, I suggested another set of primitive lattice vectors. Okay, I suggested another set. Here is another set. Remember from the beginning, I told you that the primitive lattice vectors are not unique. We can choose any primitive lattice vectors, but the most important thing is that they can stack the whole, they can reach any point in the space. Okay, so this is another set of primitive lattice vectors. Okay, and I want to find the angle between, for example, A1, A2, A1, A3, and A2, A3. Okay, so to do that, we say, for example, let theta 1 be the angle between vector A. I have to do it like this because I cannot write. Between vector A1 and vector A2. Okay, so we will start like this. So what's the formula? So I have this vector A1, this vector A2, and I want theta to be the angle between them. So what's the formula? The formula is cosine of theta 1 is equal to vector A1 dot vector A2 divided by the absolute value of A1 plus the absolute value of A2. Right? Okay. So let's continue. What's the dot product of A1 dot A2? So I have A over 2, A over 2 over here. So I have A square over 4. And then I have 1 times minus 1. So that's minus 1. Plus 1 times 1. So that's a 1. Plus minus 1 plus 1. So that's a minus 1. Okay. So this is what I have in the numerator divided by what I have in the denominator, and that's square root of. So what is the absolute value of vector A1? It is square root of A squared over 4 into 1 plus 1 plus 1, right? Times So I have the square root of this one times the square root of the other one. So times square root, the other one also has, so it is a squared over 4 into minus 1 squared. So it's 1 plus 1 square is 1 plus 1 square is 1. Okay, so how much is this? This gives me minus 1 plus 1, 0, minus 1. So this gives me minus a squared over 4 divided by so here, of course, when you are studying this, you need to be using the pen and writing these square root in the proper ways. Okay, then you can see it clearly. Now it's a bit messy because it's not clear to you what's happening. So I have here now square root a squared over 4 times 3. So this is a square root of 3a squared over 4 times square root of same thing, 3a squared over 4. And this gives me minus a squared over 4 divided by square root of 3a squared over 4 times the square root of 3a squared over 4. So that's 3a squared over 4 now a squared over 4 cancels a squared over 4 and I get minus 1 over 3. And what is the angle whose cosine is minus 1 over 3? That's theta. So theta 1 is equal to 109 degrees. If we take now theta 2, if we take now theta 2 to be the angle between A2 and A3, for example, I will get the same value. And if I can take theta 3 to be the angle between A1 and A3, I will get the same value. So you should do the math yourself, and you should verify yourself that I will get the same answer. Okay. Another simple exercise you can do is using the primitive lattice vectors that I discussed in the lecture, because these are different primitive lattice vectors for the BCC. Go back to the lecture on the primitive lattice vectors of BCC. Check what are the primitive lattice vectors given in class. Okay. And as an additional exercise, you can try to measure the angle between those ones. Okay. Of course, they will be different than this one. Great. Let's move on. Over here, you can find the solution. Okay. Now, consider a face-centered cubic lattice. So this is a face-centered cubic lattice with a lattice constant A. Again, with a lattice constant A, it means the edge of the cube is A. Find the angle between each two primitive lattice vectors, given that the lattice vectors are, so here, these are the ones given in class for the FCC. Okay. So again, do it yourself and prove that you will get theta will be equal in all cases. So A1, A2 will be equal to A2, A3 will be equal to the angle between A1, A3, and all of them will be 60 degrees. So you can do this yourself. Okay, so let's move on. So here we need to determine the Miller indices of each plane or family of planes represented in the figure. Here, before I continue, I just want to remind you that these are planes, okay? And these planes, they are not, it's not like only this plane has, if this plane, for example, what is this plane, the first one? it hits the x-axis with 1. It doesn't hit the y-axis. It doesn't hit the z-axis. So it's 1, infinity, infinity. It's 1, infinity, infinity. So the Miller indices will be 1, 0, 0. Okay. So 1, 0, 0 is parallel to 2, 0, 0 is parallel to 3, 0, 0. So feel free to move the plane if you feel that you are stuck. So for example, now you will see what I mean. So this is part A. Now, part B. Remember that to find the Miller indices, you find the intercept and then you do the reciprocal. Okay. If there is no intersection, if there is no interception, if the plane doesn't cut a certain axis, then you put infinity over there. Then it means that the plane is parallel to that axis, then it is infinity. Okay, so you put infinity. Now let's do part B. So where does it hit? This plane over here. Okay, this plane over here. I cannot work with this plane over here. It's not very clear. This one is clearer. So over here, what's happening? I have this point. Why I cannot work with this one over here? Why I cannot work with this one over here? Okay, because it hits all the x-axis. Okay, I can put infinity along the x-axis. It hits all the y-axis. I can put infinity along the y-axis, but it hits the z-axis at which point? It hits it at point 0. Now, if I take the reciprocal of 0, 1 over 0, what will it give me? It will give me infinity, and there is no plane with Miller indices infinity 0, 0, or infinity 1, 1, or whatever. So I have to take another plane parallel to it. I shift it so as I can work with it. Okay, so now I will not work with this one down here. I will work with this one up here. Okay, now where does it hit? It hits the z-axis at 1, right? It is parallel to the x-axis, so infinity, and it's parallel to the y-axis. So I have infinity, infinity, and then 1. So the Miller indices are 0, 0, 1. So this is B. Let's do C. Okay, C, it doesn't hit the x-axis, so infinity. It hits the y-axis at 1, and it hits the z-axis at 1. So I have infinity, 1, 1. So the Miller indices are, I just take the reciprocal. So this will give me 0, 1, 1, as simple as that. Some of them are simpler than others. Okay. Now this one, for example, is a bit difficult to visualize. If I come to do it, I will see it hits part D. So let's do it here. So D, the drawn plane hits the z-axis at 0, right? It hits here the z-axis at 0. It hits the y-axis at all points. So I don't have a problem along the y-axis. It's infinity. Okay, the x, it's not clear. But the biggest problem is that it hits the z-axis at 0. And now if I take the reciprocal of 0, I will suffer with infinity. So I have to shift this plane. Okay. And the best way to shift this plane is backwards. So shift the plane backwards along the x-axis. Okay, so now just imagine that I'm shifting this plane backward along the x-axis. Then I will see that it hits the x-axis at -1. It does not hit the y-axis, so it's infinity. And it will hit the z-axis at exactly this point over here. If I shift this plane backward, okay, just as it is, if I just shift it backward, it will hit the x-axis at -1. It will not hit the y-axis, it will be infinity, and it will hit the z-axis at 0.1. So I will end up with Miller indices, 1 bar, remember, 1 bar, infinity will give me 0 and 1. So this is one of the not very easy to see Miller indices. Part E, this is one of the simple ones. So it's hitting at the x-axis at 1. Let me change the color. Why only blue? So it's hitting here at 1, it's hitting here at 1, it's hitting here at 1. So it is very easy. Part E is simply 1, 1, 1. So the indices are 1, 1, 1, just the reciprocal of that, right? Now part F, I will leave it to the end because we have to do a little bit of some tricks like in D. So let me leave F till the end. Let me do G. So G, it hits the x-axis at half. It hits the y-axis. It doesn't hit the y-axis, so infinity. And it hits the z-axis at 1. So the Miller indices are 2, sorry, we don't put anything. So 2, 0, 1. Okay, and the last one, H. H hits the x-axis at half. It hits the y-axis at half. And it hits the z-axis at 1. And this will give me 1, 1, 2. As for part F, I will leave it for you to play with. I will just give you a hint. So what's happening here, so before I give you the hint, what's happening here is that it hits, you can see over here, it's hitting x-axis, y-axis, and z-axis at 0.0. So we cannot deal with this. So hint, shift it downward along z-axis. Okay, just shift it one step downward along the z-axis. You will get the answer to be, so this is part F, you will get it to be 1, 1, 1 bar. Okay, so do it on your own and see how you can get it. Now, we are not done here. Let me erase. Okay, so sketch the planes with indices 1, 2, 3, 3, 2, 1, and 0, 0, 1. So let me do some of them. So we have x-axis, we have y-axis, and we have z-axis. Okay, and let's take this point here to be 1, and this point here to be 1, and this point here to be 1. Okay, so I have 1, 2, 3, 1, 2, 3. So I will write in part 2. Part 2. So if I have the indices, if H, K, L equal 1, 2, 3, implies it intercepts the x-axis with 1/2, x-axis with 1/2, y-axis with, x-axis with 1, y-axis with 1/2, and z-axis with 1/3. So I come here now, and I choose the points. So along the x-axis, if this is here the x-axis, and this is here the y-axis, and this is here just as the conventional ones. Okay, so my points will be this one. It intersects at point 1. The y-axis at 1/2, so it should be somewhere here at 1/2. And the z-axis at some 1/3. So let's assume it's here. You can draw it properly on your notebook. and then I connect the dots. So this is my plane. Okay. So to do 3, 2, 1, I do the same. I say HKL is a 3, 2, 1. It means that it hits the x-axis with 1/3. It hits the y-axis with 1/2. It hits the z-axis with 1. And I draw my x-axis, y-axis, z-axis, and I put over here 1/3 and over here 1/2, and then here with 1, and I connect the dots. Okay. Let me draw with you 0, 0, 1. So again, I need x-axis. Let's do it in red, so as we keep the same color. So this is x-axis, this is y-axis, and this is z-axis. Okay. So 0, 0, 1, it means it doesn't hit the x-axis, it doesn't hit the y-axis, it only hits the z-axis at 1. So let's take this to be 1. Okay, and now if I draw this plane, it will be something like this. It's parallel to the x-axis, it's parallel to the y-axis, right? And I draw the plane. This is, and you can color it. Okay, so this is the plane 1, 0, 0, 0, 1. Okay, great. I hope you are finding the exercises easy to deal with. The last thing, this is a formula that I asked you last time to prove. And this is the spacing between two adjacent planes, okay? So I want to find the distance, that is the distance between two adjacent planes, okay? I don't know if you tried to do it or not yet. I'm gonna give you hints. That is what is the way to do it. So the first thing you have to do is you have this plane between two adjacent planes, and here actually for a cubic lattice. Okay, so we will say that the plane is HKL. Okay, you need to find the equation of the plane HKL. Okay, this is the first step. So you find the equation of the plane HKL. Then, so this is step number 1. Step number 2, and this how to do it. How to do it? Just review or Google it for revision. So review how to find equation of a plane if I have 3 points. Okay, if I have 3 points, because if I have HKL, it means I have the 3 points that hit the x-axis and the y-axis and the z-axis, right? So I have the first point whose components are 1/h or a/h, 0, 0. The other point hits at a/k, the y-axis, so it has components 0, a/k, 0. And the third point, it's along the z-axis, which has components 0, sorry, a/z. Okay, so you have these 3 points, and you need to find the equation of a plane that has these 3 points. Then the second step, take any point on the plane. Okay, take any point on the plane. For example, take the point which has the components. So for example, take the point which has the components a/h, 0, 0, because this is the point that hits the x-axis. It is on the plane. So for example, take this point. Okay, then find the distance between point, so let's call this point P, for example, between P and the consecutive plane. So if this is here HKL and you find its equation, it must be something in terms of A. The new one will be A plus 1. Okay, it will be something, but instead of A, there will be A plus 1. And here is the formula. So the distance between a point P, which has components x1, y1, z1, and a plane which has this form is given by this formula. So I'm giving you hints in order to be able to prove that the distance between two consecutive planes is indeed A divided by square root of h squared plus k squared plus l squared. Okay, so try to do it, and maybe in the live session next time we will do it together if I didn't have any other arrangements. Okay, but you need to try to do it on your own. So that's it for today's lecture, and we will talk next week.